Today I'll talk a bit about one of our approaches to get higher lifetimes and not just higher speeds out of our steels. But first, a bit of context. So high-speed steels. High-speed steels are known or have the name from the application which is in metalworking of metals, or which is in metalworking where high speeds are involved, just drilling, machining, or milling. Basically, they have extremely high strength, as you can see here. And even have some ductility left, and what's usually referred to as reasonable toughness. Of course, once fatigue is involved, that game changes, as is here pretty illustrative. For this specimen, we introduced a very small artificial defect of microstructural size, and after cyclic loading and tension, just after a few thousand load cycles, failure occurred at loads that are far below what we'd expect from the ultimate tensile strength. Of course, with fatigue, that's what we'd expect. Still, it raises the question, what's the point of having all this mechanical strength if it can't be used at all? Which leads us to a fatigue-centered approach in furthering the high-speed steels themselves, which is very difficult if you try to do it with changes in the chemical composition, because just a small change in the chemical composition can significantly alter the outcome of the final product without you having any real option of finding out beforehand. That's highly time-consuming and very ineffective. So what we tried to look at was at the general heat treatment process, which is complex enough in and of itself. As you can see here, there's quite a change in the phase composition during that whole treatment process. And one of our approaches was to just try to retain a bit of the austenite that's usually intentionally removed during the tempering heat treatment itself. We tried to retain that until after the heat treatment and see what it would do with the fatigue behavior. We started out with a conventional commercial standard state as it's used in the industry, which has no retained austenite and impressive Rockwell C hardness number of 66 HRC, so about as hard as it gets. Then our first material state that we used with retained austenite was simply achieved by lowering tempering temperature below the secondary hardening heat treatment, just so that the secondary hardening precipitation, which usually occurs and destabilizes the retained austenite, so that it transforms during the full heat treatment, did not occur. And we had about 15 volume percent of weight percent of retained austenite left after the full heat treatment. With our final material state, we just deviated or adapted the quenching and partitioning heat treatment, where we replaced basically the final tempering step with a partitioning step. By that, we achieved a similar amount of retained austenite in both retained austenite containing material states and the same composite hardness for all of our material states. So working with that, we moved on. The first test regime, tensile tests, for which we used two test setups, one at the German Institute, Electron Synchrotron Institute, DESI in Hamburg, and one at our local laboratory, because the setup that we had available at DESI wasn't ideal for high-strength materials due to the threads of the specimens and also the extensometer which was mounted on the load frame, and thus the strain measurements weren't as accurate as we'd have liked. Looking at the stress-strain curves we see that a lot has already changed and happened in one high-speed steel grade just by retaining a bit of austenite. Mostly, of course, the ultimate tensile strength is lowered, but what's also pretty evident is that this transformation strengthening effect occurs in the quench, tempered, and partitioning material state until a similar ultimate tensile strength as with the low tempered material state. If we add also the retained austenite contents that we got from monitoring at DESI, you can see that this agrees quite nicely with our stress-strain curves, and we can also see that the retained austenite content decreases below the reasonable detection limit of 2% until failure of the specimen occurs. So far, all is well. That's still not the only thing that we got out from our DESI test data, because from the in situ accelerated transmission data, we also derived the lattice parameters. We saw a kink in the lattice parameter of the austenite phase after onset of martensitic transformation. We just thought, well, maybe that's because the austenite that transforms last is a bit different from the one that transforms first. And by slightly modifying the well-known Dyson equation, we estimated the carbon content in the austenite phase. Please keep in mind that that's just a general estimation. So the trend is probably correct, but anything more than that requires further evidence. Still, what we can see is that the final austenite that's left at the moment of specimen fracture seems to have a higher carbon content than the one that is transformed here first. This indicates that there's a difference or heterogeneity in the stability of the resident austenite islands in our material state, which is to keep in mind later for the fatigue results. So our main test regime was, of course, fatigue testing, for which we did the pre-cracking intentionally before the full heat treatment to reduce or to diminish the effect of or the load history from pre-cracking and compression, which is known to affect certain fatigue properties for high-strength materials. The specimens we used were single action spent specimens. You can see here after full heat treatment before the fatigue test. And our test setup was an 8-point bending test setup so that we could apply a wide range of load ratios ranging from 0.1 to -5. Also, we monitored fatigue crack extension with the direct current potential drop technique. So here you can see a basic load regime as we applied for pretty much all of our specimens. If you're wondering why the red line for the repeat test is a bit different from the first line, that's because we started at a different stress intensity factor range that was moved in the amplitude by half the step size here, so that we basically got improved resolution by looking at the same fatigue properties at different points. So if you look, for example, at the cyclic R curve, which is usually the function of stress intensity factor range at which crack arrest occurs, dependent on the fatigue crack extension, we can see that if we move along the same cyclic R curve in a material state at different stress intensity factor ranges, we have twice the resolution with just 2 tests instead of and also, of course, can get an overview of the experimental scatter, which is quite important in fatigue testing itself. The same is true for fatigue crack growth diagrams. We get a good overview over the long crack threshold, also Paris regime, because that shouldn't change with our testing approach. And this brings me, because we're short on time, to the results. For the cyclic R curves, you can already see that, especially for the quench tempered and partition material state, the R curve itself seems to have a steeper slope towards the final plateau, and also a higher plateau that is also indicative of the long crack threshold. So whereas the other 2 material states aren't quite distinguishable, especially not with the scatter that we just have to live with. If we look at the other fatigue test results at the stress ratios with a compression part, you can see that the trend actually holds and even increases, so that we have really a significant increase, especially in the long crack threshold at R equals -5 testing for the quench tempered and partition material state, but also for the low tempered partition material state. This is particularly important to note because for high-speed steels, that particular stress ratio is actually the one that's most application relevant. So quite a nice and encouraging result. But if you look at the fatigue crack growth diagrams, picture changes a bit, because as you can see here, the slope in the Paris regime is much steeper than for the reference material state for both austenite containing material states, which isn't ideal, to say the least. And if we look at all the other fatigue tests, you can see that basically this remains fairly consistent, although for the quench tempered and partition material state, we can see that the relative increase in steepness of the slope in the Paris regime, that is the Paris exponent, decreases with increasing shift to the compression range. So again, that's a bit encouraging that maybe not all is lost. Now, this is just a final interpretation of those fatigue results that we tried based on a simple transformation zone concept, here illustrated by the example of the von Mises deformation criterion. And if you look here, you can see that of course, based on the tensor of the stress strain behavior that you've seen before, that the transformation zones or plastic zones differ quite widely or quite significantly for each material state. If you look here at the quench tempered and partition material state, you'll notice that there's a gradient, a color gradient, that should represent the behavior that we've seen before in the stress strain behavior, and then especially in the behavior of the retained austenite content and its associated carbon content, that is this differences, this heterogeneity in retained austenite stability. Essentially, that means for any given stress field or transformation zone, on the outer edges of this transformation zone, only a small fraction of retained austenite is actually capable of transforming, whereas that fraction increases with proximity to the fatigue trap, or is at least expected to. If you look then at the general mechanisms that are known for transformation-induced crack closure to see if that's actually what's happening, of course, the one that's most simple is just transformation-induced crack closure based on the compressive residual stresses that are introduced by martensitic transformation and associated increase in volume, which leads to crack tip shielding. Still, that's extremely hard to prove, which is why we looked at the second kind of mechanism that's known for this kind of transformation-induced crack closure, which is basically crack deflection based on an asymmetry in deformed or in the present compressive residual stresses ahead of the fatigue crack tip. And that, if the crack is deflected out of plane, that should be evident on a fatigue fracture surface. So naturally, that's what we looked at. First, I just looked at a very small localized part of the microstructure of each specimen, tilted at 20 degrees, fed it into a photostereochrometrical software, and got a 3D model of the fatigue fracture surface because it looks really nice. And here, also very flat. So that's our reference state. Seems that crack propagates quite nicely in one plane. That's a different case if you look at the low tempered material state and also at the quench tempered partitioned material state, which are both increasingly rougher. So there's also a ranking in fatigue fracture roughness, in fatigue fracture surface roughness. And I've also tried my best to get a bit more statistics by doing laser confocal roughness measurements on a line from the pre-crack towards final fracture. So with increasing fatigue fracture index, with rising fatigue fracture, fatigue crack extension, and on far larger measurement fields to have a bit more quantity in our results. And the trend is replicated, but nice. And if you compare it to the actual fatigue results, here an example of just the cyclic R-curves, you can see that the ranking or the trend really seems to agree in quite nice agreement. That's basically it. And the key point I want you all to remember is that you don't need to develop a fully new steel grade. It's really there's really quite a lot of potential in just adapting or tweaking the heat treatment process in such high strength steels to get completely new phases into the material, which might have quite some beneficial effect on the actual fatigue behavior. And that's it from me. And if there are any questions, feel free to ask.